In this class, we're going to finish up some of our discussion on multi-electron atoms, and then we're going to begin the discussion on properties of molecules. Our primary source for the material for this portion of the lecture is the textbook by Crane, a little bit from chapter 8 with respect to atoms, and then chapter 9 on molecules. Other material can be found in the quantum physics textbook by Iceberg and Resnick predominantly. The specific topics that we're going to focus on today are to finish up with multi-electron atoms, in particular to discuss spin and angular momentum in a situation where you have more than one electron on an atom and the resultant properties. And then we're going to begin a discussion of covalent bonding. I've renamed it here according to the primary mechanism, which is binding by quantum tunneling. And for this class, we're going to focus on a very simple, and things are complicated, on a simple complicated system, which is two protons with one electron. So it's the hydrogen ion plus ion. Um, and then in the next class, we'll continue with molecular properties and talk about a real, regular, normal molecule that can be found in nature, the hydrogen molecule, and other bonding types. So first covalent bonding, then ionic, metallic, van der Waals, and some of the properties of materials that follow from those bonding types. We have talked about the properties of an electron, which has orbital angular momentum and spin angular momentum, spin, both of which give rise to a magnetic moment. When we have multiple electrons in a system, then we have to be thoughtful about the way that we add the angular momentum and the spin angular momentum, so orbital angular momentum and spin angular momentum, because these things do control the magnetic properties of the atoms and help to determine how electronic states are actually going to fill. So we have electronic states that are various energies, but we have to pay attention to angular momentum rules as we fill those states, that is, exchange symmetry rules in particular. So we're now going to denote the angular momentum for a group of electrons as capital L, and the spin angular momentum for a group of electrons as capital S. And the orbital angular momentum first, we'll talk about that first, is the vector sum of the orbital angular momenta of each of the electrons in the system. And then each of those electrons will have a particular vector angular momentum that is determined by the way in which states fill the Pauli exclusion principle, which follows from exchange symmetry. For two electrons, I'm just rewriting what I said in words here, the angular momentum of two electrons together is the vector angular momentum for the first electron plus the vector angular momentum for the second electron in the system. And the magnitude of the angular momentum is equal to the square root of the magnitude of the angular momentum quantum number times the magnitude of the angular momentum quantum number plus 1, square root of that, times h bar. So this would be for each of the electrons in the system, and then we pay attention to the direction of the angular momentum vectors in order to add them together. Similarly, the spin angular momentum is a vector sum of the momenta of the electrons. In this case, spin angular momentum is just going to be up or down. That's what specifies the direction here. And so for two electrons, we add those up together, and the magnitude of each of the spins is this, and then we have to add the vectors appropriately. I'll have a little graph of that way to add these sums in a moment. But here are some rules. The maximum value of the total angular momentum, remember now we're talking about adding these momenta together as vectors, and we could start out and say that the angular momentum for the two electrons might point in the same direction, in which case the maximum sum for the two, the quantum number for the two, is electron 1 angular momentum plus electron 2 angular momentum. So let's say one of the electrons is in an L equals 2 state, and the other one is in L equals 1 state, and therefore the sum of the two would be 3. The minimum value for this pair of electrons for the total angular momentum is when one of the momenta is opposite to the other one. So I could have an L equals 2 state, but that L equals 2 state is pointing in an opposite direction from the L equals 1 state, so I'd have 2 minus 1, and the minimum value of the total angular momentum then would be 1. So the permitted values that we can have in this system for that angular momentum range from the minimum value to the maximum value. And the z component then of the angular momentum is found from the sum of the z components of the individual electrons, so the projection of the angular momentum onto the z-axis. Again, we find the m sub l's for each of the electrons in the system, and then we just add them. Remember, m sub l can be negative, so they can point with one another or against one another. One note, we can find this by doing these sums carefully for multiple electrons working through a system. I'll just note here that all filled subshells have total angular momentum equal to 0 and total spin equal to 0. Related to this is a concept you've heard of before in a chemistry class called Hund's rules, which allow us to predict the energy order in which states will fill, which state gets, as we work our way up through the principal quantum numbers and the angular momenta, which states are going to fill first. And here's a set of rules, approaches that allow us to figure out which states fill first as we put electrons into a system. First, you find the combination of spins that yields the maximum value of the total spin magnetic number. What that is doing is putting electrons into different spin states so that, I take that back, is putting electrons very frequently into the same spin state if possible, because that puts them into a symmetric spin state so that the angular momentum states, the space states, become antisymmetric. And when that happens, the electrons spend time further apart, and as a result, the Coulomb repulsion or the Coulomb energy for the system decreases. So now we put the electrons into the state that yields the maximum value for the total spin, and then for that value of the total spin, we find the combination of angular momenta that is a maximum consistent with the Pauli exclusion principle. That is, that I have to have an antisymmetric total state, and so we'll have to pay attention to what angular momentum we put the electrons into. So here's an example, because those were just complicated words a moment ago. Let's choose a particular atom, nitrogen. And the electronic configuration then is going to be looking at the principal quantum number. We first fill one, and then we fill the two states, okay? And then the question is, how are they going to go into the S and the P states? So we fill the S shell because that's at lower total energy than the P shell, subshell, and that leaves us with 3 electrons in the p orbitals. So the spin and angular momentum for these filled shells, 1s squared, 2s squared, is 0. So we don't have to include those in any magnetic computation that we do. Now, I have 3 electrons here. The maximum value of m sub s then is 3 halves. For example, all the spins pointing in the same direction, up. All right. The maximum magnitude of m sub s is 3 halves, but it's going to point, it can point in a direction of plus 3 halves, plus 1 half, minus 1 half, and minus 3 halves. All right. Since all the spins are the same, all right, the electrons must be different in different m sub l states. According to our rule on the previous page, the first electron goes into the highest angular momentum state, which is the plus 1 state. Second electron will go into the next m sub l state. The highest one that's left is the 0 state. And the third must go into the minus 1 state, m sub l equals minus 1 state. They must go into different states, otherwise I can't make an antisymmetric wave function. Or another way of putting it is that I can't put 2 electrons with the same spin, they're all the same here, I can't put 2 electrons with the same spin in the same m sub l state. So that tells us how the electrons must be organized in nitrogen. In oxygen, we've added 1 electron to the system. Once again, the filled shells have angular momentum and spin of 0. The maximum value now of m sub s is 1, because the first 3 spins point in the same direction, but then the next state that we could possibly fill is going to have a spin in the opposite direction. We'll be forced to be in the opposite direction. So the first electron goes into plus 1. The second electron must go into a different m sub l. Highest one is 0, same as before. Third goes into the minus 1 state. The fourth has to go into the plus 1 state, and as a result must have opposing spin, because I can't put 2 electrons with the same spin in the same state. We're going to talk about this in class. And here's just a graphical example of how one adds together, in this case, and in a moment I'm going to talk about it, adding orbital angular momentum and spin angular momentum. They are each vector directions with projections onto the z-axis. And if the 2 vectors point in the same direction, L and S point in the same direction, then the total angular momentum is L plus S. I have different possible projections for the spin angular momentum. In this case, the spin, let's say for this example, would be 1. And so let me think of it. The spin might be 2, 4 electrons, all with the same spin, for example. Might add up to 2. And therefore, I can get a projection onto the z-axis of 2 1, 0, -1, -2. Okay? And in this case, the angular momentum is larger, and as a result, when I'm done adding these two together, if they are together, it's just L plus S. If they are in opposite directions, then the minimum magnitude is the difference between the two. And for this combined L plus S, it will now have different projections on the z-axis. Now we're going to shift gears a bit and talk about bonding in molecules. Over the next couple of classes, we're going to talk about a variety of bonding types. This time around, I'm just going to introduce the idea of covalent bonding and how one can think about covalent bonding. We'll talk about ionic and van der Waals bonding in the next class. In a real molecule, the simplest covalent bond is H2 plus, right? So just one electron and two protons. And we're going to deal with this system in approximation, and I'll just tell you the name of the approximation here and then talk about it later on when we actually get to the molecule itself. The idea here in this approximation is that the mass of the electron is much, much less, 2,000 times less, than the mass of the protons. And as a result, the electron wave function will very rapidly rearrange when the nuclei are moved. And so we can analyze this problem as though initially, to get the wave functions and energies, as though the nuclei are fixed in position. Those positions will actually later be established by minimizing the total energy of the system. But for our purposes here, we just assume a distance between the two nuclei and then solve for the electron energies. That approach is called the Born-Oppenheimer approximation. But first, we're going to talk about a very simple physicist-style model for molecular behavior. And in our model, quote-unquote model, we'll take a system in which we have a one-dimensional system in which we have two finite square wells. So this is the potential on this axis. The energy of the bound state will be somewhere in here, for example. And what we want to think about is what the wave functions might look like for this system and how they might depend upon the distance between the two quote-unquote atoms. Because our molecular system is symmetric about the center, we can conclude mathematically that the wave function that is going to result from that symmetric potential is going to either be symmetric or anti-symmetric about the center. Now, I just want to clarify at this point that there's an unfortunate overlap in words. That is, that right now we're using the phrasing symmetric or anti-symmetric about the center to mean an even or odd function about the center. And just a few minutes ago, we were using the words symmetric and anti-symmetric to be the properties of a joint wave function of two electrons under exchange. That is, does the sign of the wave function change when we switch one electron for the other? Here, we're talking about the even or odd properties of the wave function about the center. Because the wave function has that simple symmetric property, it turns out that the method that we developed, the finite difference method that we have already for the Jupyter notebook that you worked on, right, is the same method. All we have to do is change the potential in it. So during class, we'll actually take the Jupyter notebook and work through some examples with the Jupyter notebook. So you can see how these states actually change as we change the distances and the widths of the potentials here. Okay, so let's look at the overall behavior just sort of to get an idea. If I have two wells really far apart, then I can think about the wave function for the system as basically being the wave function of an electron on one of the wells and the wave function of an electron on the other of the wells. For the kind of system that we were talking about, the hydrogen system, the electron is, if we haven't measured it, it simultaneously has a probability of being here and a probability of being there. So this is the wave function for one electron, all right? And when we solve the Schrodinger equation for this system, we do find that it looks like, that the wave function looks like a single electron state here and a single electron state there, with the amplitudes modified in order to make the probability of finding it somewhere 1. We can equally well find a solution where the wave function on one of the atoms, one of the wells, has the same amplitude as on the other well, but is out of phase. And remember that when we square these wave functions, we're going to get the same probability distribution here as we have there. So those are two different solutions. And when we square out the probability density, it's going to be, they're going to look the same. So the energy levels for the electrons in this system are going to just be energy level for that guy alone and energy level for that guy alone. We add them together half the time in each one. And so the energy for an electron in this system will be equal to the energy of one of these states. Now when we bring the two wells closer together, and if we were to just plot the wave functions that we had before, then we would find that for the space symmetric case, that the new wave function, which is the sum of those two wave functions, is high in the middle, all right? It doesn't quite go to 0. Whereas the antisymmetric case, antisymmetric about the center between the two wells, goes to 0 between the two, and then is flipped with the opposite phase on the other square well. So now the symmetric and antisymmetric wave functions, when squared, actually look different. Okay, this one goes to 0, that one does not. If I put them closer still, then this one clearly doesn't go to 0, and this one has to go to 0. So again, the wave functions will look very different from one another. And then when I put the two wells so that they're just touching one another, we can't put them inside one another, but so that they're just touching one another, then the lowest energy wave function for the just touching state, when it is symmetric about the center, looks like the n equals 1 level, the ground state of a single wide well. And the the next state, which is antisymmetric about the center. Remember, these came from the sums of the wave functions on each of these wells, right? But now, when I put the two together so that they're touching, this state here looks a lot like the n equals 2 or the excited state. So at this point, very clearly, the symmetric state and the antisymmetric state have different energies. And I just have a slide in here that emphasizes that. The case B, this one here, looks like the n equals 2 level in a single wide well. If we make a sketch of how the energy for those two states, what it looks like, then we would see something like this. When the two wells are very, very far apart, then the total energy of the system is equal to the energy of an electron in one of the wells. Half the time in one, half the time in the other. Energy in each of the wells. So energy in one of the wells. Then as we bring them together and we get overlap between the wave function on the left well and the right well, then the shape of the symmetric and the antisymmetric wave function begins to be different, and the symmetric case goes down in energy. Ultimately, the symmetric case would go down to the point, if the two wells are just touching, so that the energy of the electron in the symmetric case has gone down to 1/4 of the original energy because I doubled the width of the well. These are finite wells, so we don't quite get there. And for the antisymmetric case, where the wave function goes to 0 at the center of the two wells, then you might expect then that the energy is just going to remain at the same level, okay, except for the fact that when we've actually brought those two wells close to one another, then we're going to force a change in the shape of the wave function from what it was for each, for two separate wells. I had a wave function which, as an example, let's see, on a single well will look like this. It extends outside the well, but when I touch it to the next well over, this wave function is going to be forced to come down. So it actually changes more rapidly when the two wells are touching one another. And so the energy goes up a little bit, as we see there. All right, so now let's talk a little bit more about hydrogen. For the actual situation where we've got hydrogen 2 plus, all right, if we look along the axis between, so this is a distance along an axis where I've got nucleus 1 here and nucleus 2 there, then the potential that the electron sees looks like the Coulomb potential for each of the two added together. And these two nuclei are separated by a distance capital R, which will be determined later on. So along one axis, it looks like this. All right. In fact, we have to solve this whole problem in 3 dimensions. So this is not trivial. All right. I can't simply use spherical coordinates because, of course, we will. We can't use spherical coordinates in a simple way because each of these potentials is centered at a different origin. We can think about this similarly to the toy molecule that I talked about a few minutes ago, where we look at what the wave function looks like on one of the atoms and the wave function on the other of the nuclei, rather. Okay, so two nuclei in the molecules. And in one situation, one extreme situation, I have an electron probability for the potential that's given here. And so this is that exponentially decaying electron wave function for, let's say, a positive phase. And if the wave function on the other nucleus is of the same phase, then the overall wave function looks like this. And if the wave function on the two nuclei is of different phase, then you can see that this one is forced to go through 0. So as a result, when we square this out, we're going to get a probability density for the antisymmetric case, which goes to 0 between the two, and for the symmetric case, where the probability density does not go to 0 between the two. As a result, for the moment at least, ignoring the details of the actual electron charge, and we're going to have to include that in our calculations, and ignoring those details, we would conclude that this state here, the plus state, the symmetric state, is going to be a lower energy than the antisymmetric state, just like the toy example that we talked about a few minutes ago. But then in addition, we will be concerned with the actual Coulomb interaction, because electrons are negative and protons are positive. All right, I promised that I'd say something about the Born-Oppenheimer approximation, and here it is. We treat the nuclei as though they are fixed in position. So nucleus 1 is at position R, capital R, from the origin. Sorry, R over 2 from the origin. Nucleus 2 is capital R over 2 from the origin, but in the opposite direction. So the two nuclei sit on opposite sides of 0 for the coordinate system. There's only one electron in the system, so we are concerned now with the kinetic energy of the electron, with that, and that kinetic energy should include the full Laplacian. Okay, the Coulomb energy of the electron with respect to one of the nuclei, the Coulomb energy with respect to the other nucleus. Right, so these are Coulomb potential terms here, and then there's a Coulomb interaction in the opposite direction between the two nuclei. They repel one another. So negative potential, positive potential. And that will yield the total energy for the system. And again, in this case, we are taking R, little r, to be the position of the electron, or the electron coordinate system, not the position of the electron. We're going to solve for the wave functions. And capital R to be the positions of the nuclei, and we take the positions of the nuclei to be fixed when we calculate the wave function. Now comes the hinky trick, the approach to try to figure out what's going on. Because in systems like this, actually the only way to figure out what's going on properly is to fully solve the Schrodinger equation numerically. But what we're going to do here is get an idea for what goes on so that we can make plausibility arguments for what happens in this molecule and in others. At this point, remember, we are talking about covalent bonding because the two nuclei are the same. and the electron doesn't decide which of the two to be on. It's on both. We, as an approximation, take the solution to be the atomic orbitals on the original atoms. So these were hydrogen. This is the 1s orbital on atom 1, nucleus 1, and the electron 1s orbital on atom 2. So the even solution for this particular case, right, is wave function on atom 1, wave function on atom 2. And I am aware that I'm sort of regularly and unfortunately switching between the designation of which of these is atom 1 and which of these is atom 2. It really doesn't matter. I just have the two situations. I could call this atom A and atom B, for example. In fact, better still, I'll call this atom A and atom B. So we haven't solved anything here. All that we've done is to say, hey, you know, I think maybe my final wave function is going to look sort of like the wave function of the electron on one atom plus the wave function of the electron on the other atom. And another combination that yields solutions to this problem is one where I subtract the wave function on the other atom. So that would be the minus solution. Plus would be plus on one, plus on the other, and minus, which would be the odd solution, different signs on the two sides of 0, would be plus on one, minus on the other. This approach has a fancy name. In chemistry, it's called the linear combination of atomic orbitals. And it's used so frequently that they just give it an acronym, the LCAO approximation. Linear combination of atomic orbitals. So what does the potential look like? We looked at a picture of it before. It's a double well, like what we looked at before. And I did identify the atoms as atom A and B here. All right. What we're going to seek is the total energy of the system, and we want to minimize the total energy of the system. So what goes into the Hamiltonian will be the kinetic energy of the electron. We ignore the nuclei. All right. Kinetic energy of the electron, which is found by operating the kinetic energy operator on the wave function for the electron. Then there are potential energies, which come from operating the potential energy operators on the wave function. The potential for electron with respect to its position of atom A is this one, depends upon the distance from atom A. And for atom B, it's distance from atom B. And then the distance between the two nuclei because there's a proton-proton repulsion. So those are the terms that are going to go into the Hamiltonian for the simplest approximation here. This one's a bit of a mess, but it's not all that bad. We're going to find the total energy for the system, and so we're going to calculate the expectation energy for the even case and the odd case. All right. So we're going to put even wave function and odd wave function in here, and then we're going to calculate the expectation value of the energy using the Hamiltonian. I have those four terms. The kinetic energy term, potential due to atom A, potential due to atom B, and the potential between the two of the nuclei, right? And my symmetric wave function is psi A plus psi B. That is the original hydrogen wave function on atom A, original hydrogen wave function on atom B, and we either add or subtract them. We'll sort of follow through on the plus signs here. And over here, same case, all right, the symmetric combination or even combination of the two. What we now do is to actually go ahead and expand this, looking at all of the potential terms that would contribute to this thing here. Remember, you got psi A plus, psi plus or minus, I say psi, but it's actually phi, phi B, phi A plus phi B, for example, here. So we're going to begin to pull that apart in ways that I hope will make the outgoing energy and physics a little bit more clear. So let's now look at this operating on that, and we're going to pull this apart in a certain way. I'm going to take these two terms here, T plus VA, and operate them on phi A. And I'm going to take T plus VB and operate them on phi B. And the reason for that is that the calculation of phi A T plus VA phi A, so just taking that first term there, yields the energy of an electron in the original state on atom A. And phi B operating on this is going to give me the original energy of an electron on atom B. So I can make substitutions in here. That is that T plus VA phi A is energy phi A, energy 1 of state 1 phi A, and T plus VB operating on phi B yields energy 1 phi B. So this bit over here turns out to be easy to evaluate with our approximation. But when I just picked out those terms, I left some terms out that we hadn't taken care of yet. I have VB operating on phi A and phi B, on phi A. I've got VA operating on phi B. That was not included. These mixed terms were not included. So again, all we're doing is expanding this thing out to take apart and put certain terms together. And when I do that, I have phi A potential B plus the Coulomb potential for the two nuclei, all right? Phi A, phi A, phi A. And again, we're just going through and sort of counting up all the terms, all the product terms that we could have. Phi B, but with potential A, phi B. Remember up here it was just VA phi A, right? But now it's the potential due to atom A, but the wave function is on atom B. And then the only terms that are left over are the crossed terms, phi A, VA, phi B, phi B, VB, phi A. All right, all of that is just sort of wave function soup at this point. All we've done is to pick things out, but there is physical meaning to these. So that I'll talk about on the next slide. As I pointed out, T plus VA operating on phi A is the energy of a state on for an electron on atom A. T plus VB operating on phi B is the energy of an electron on atom B. So that's just, remember I had a half out front, so this combination here is just the energy of an electron on a hydrogen atom. All right? But now I've got these other terms here. This one is phi A, VB, and that's the Coulomb energy for the electron on one of the atoms. So the electron's on atom A, but how does that electron that's on atom A interact with potential B? And then we're just throwing the internuclear term in there, all right? That's actually doesn't even integrate in dr because r doesn't appear there. It's just a constant that pulls out front. All right. And then, by the way, the integral for that part is just VR. Same thing here. All right, by the way, that's because phi a squared integral over all radii is 1. Similarly, for electron on atom B interacting with the potential of A. So G is the Coulomb energy for the electron on one of the atoms due to interaction with the potential of the other atom. So if the atoms are far apart, G is very small. If they're very close to one another, then G becomes large. And then this other term that we've labeled S is the cross term. I've got phi A, should be phi A star, phi B star, phi A, all right? And this tells us something about the overlap between the two wave functions, where I've got wave function of the electron on A and wave function of the electron on B. So S is the Coulomb energy due to the overlap between the electron wave functions. So here's a figure from Crane that gives us an overview of everything that is happening here. All right. As a function of distance between the two atomic cores of the two nuclei, the various energies look like this. The Coulomb energy between the two nuclei just looks like 1 over the distance between the two nuclei. So this is the distance between the nuclei on this axis, and the overall Coulomb energy for those two is going to go to 0. Okay. All the other terms in the asymptote of very large R are going to go to minus 13.6 electron volts. All right. Because at very large R, the system, no matter what the symmetry is, behaves as though it's got an electron on, half an electron on one nucleus and half an electron on the other nucleus. So at very large R, the various energies go to minus 13.6 electron volts. Okay, so what about the energy for the symmetric state? Okay, as it's going to go out to minus 13.6 when the two systems are an infinite distance apart, all right? But then as we bring them together, the overlap between those two wave functions, the fact that the electrons don't go to 0 and therefore the wave function is not as rapidly varying, so the kinetic energy is going to be lower, leads to a lowering in the energy of the system. All right, that's sort of the overall controlling term there. So the total energy of the system is going to be equal to the sum of the electron energy for the symmetric state as a function of distance between the two, and the Coulomb repulsion of the two nuclei, We add those together and we end up with a sum of the two, which looks like this term here. All right? And the important thing here is that there's a minimum. And that minimum in the sum of the two energies, Coulomb repulsion and electron energy, is about 2.7 volts lower than 13.6 electron volts. And what that tells us is that the binding energy of two protons to one another with one electron is greater than the binding energy of an electron on either split between the two nuclei or on one or the other of the nuclei when they're far apart. So the H2 plus molecule actually is a bound molecule for the system where the electron is in an even or the symmetric state, where the electron electron wave function on the two atoms is taken to be of the same phase. This calculation here actually is just that linear combination of atomic orbitals approximation. But it turns out to be pretty good. When we measure that binding energy, it's pretty close to 2.7 electron volts. So that linear combination approximation works pretty well. On the other hand, the electron energy for the case where we're in the anti-symmetric case, right? Ultimately, when they're very far apart, that energy is going to go to minus 13.6. But as we bring them together, the energy does begin to go down, but then the fact that the two wave functions, the one on the right and the left, are of opposite sign, induces more curvature, more kinetic energy to the electron, and ultimately the energy begins to come up, all right? Both due to curvature and, well, actually I'll leave it at that. Due to the curvature of the wave function, kinetic energy is going to come back up again. And then when we add the Coulomb repulsion of the nuclei, the sum of the two looks like this one here. And this energy, as you bring the two nuclei close together to one another, just goes up, meaning that the anti-symmetric case here does not have any bound state. That is, if we somehow put two protons and an electron together at this distance in the anti-symmetric wave function, they would move apart. They're going to move down this potential, right? Whereas if we did the same thing for the symmetric wave function, then we would see that they would move together and they would be bound at that energy there. All of this actually is computable at this level of this course. On the previous slide, we explicitly showed you what integrals need to be done. It's just a mess because we've got spherical wave functions on nuclei, and then our system does not have spherical symmetry. So this has to be done numerically in order to get a reasonable answer. But the linear combination approximation works pretty well and actually predicts the energies fairly well. If it didn't, then we'd have to find another approximation. In the next class, we're going to talk about the neutral hydrogen molecule with two electrons in it. And I won't talk further about this, only to tell you that that's what we're going to do in next class.